Hello students, welcome to my channel again. Thank you for overwhelming response to my channel and supporting my video lectures. So I will continue my discussion from the last lecture. In the last lecture we concluded de-Broglie hypothesis. Just some other terms are that I think we must just have the knowledge. I would be just sharing 5 to 10 minutes of knowledge regarding with the de-Broglie waves in this lecture. Thereafter, we will move to the next topic, that will be the eigenvalues, eigenfunctions, and operators that are required for studying the Schrödinger equation. We will move to Schrödinger equation later on, but in today's lecture, we would be discussing some initial basic concepts that were related with the Schrödinger equation. So before starting with this operators and eigenvalues and eigenfunctions, I would just try to give you some comparison between electromagnetic waves and the de-Broglie waves. Both of these waves just be taken different from each other. They have something common in themselves, and some differences are there also. And we would just try to have some results. We would discuss something related with the de-Broglie waves of matter and de-Broglie waves of photon. Means we would try to make a discussion on whether is it possible that de-Broglie concept is applicable to the photon also. Of course the answer should be yes, but it will create a lot of sensitive concepts. It will just try to put pressure on the brain of a person who is just curious about these things, because these are critical things, and matter on one side and light on other side, and we are trying to just formulate both of the things with one formula. Let us try to discuss first what is the comparison between de-Broglie waves and electromagnetic waves. I will be discussing both similarities as well as the differences. And electromagnetic waves are general and light is in particular, because light is also a part of it is a form of electromagnetic wave. Just its wavelength ranges between the visible region. The visible region is defined as that region of electromagnetic spectrum which can be sensed by the human eye, and that region, visible region, has a wavelength range starting from 3500 angstrom to 7500 angstrom. In terms of nanometer, this will become 350 nanometer to 750 nanometer. This smallest wavelength corresponds to violet, and this longest wavelength corresponds to red in the electromagnetic spectrum, and whole of this region from violet to red is called visible region. So below the region whose wavelength is below 350 nanometer, and the region which is above 750 nanometer, so this is called infrared region. IR region. And thereon, if we go to further beyond that, you will get microwaves, you will get radio frequency waves, audio frequency waves, power frequency waves. And if you move to the left of this region, means wavelength is still smaller than 350 nanometer, you would get ultraviolet region followed by X-rays and gamma rays. And whole of the region from the power waves, they starting from the power frequencies, then to audio frequencies, radio frequencies, then microwaves, then IR, then visible, then ultraviolet, then X-rays and gamma rays. This combined region is called electromagnetic spectrum region. So it is just a part of that visible region is just a part of the electromagnetic waves. Okay, first of all, what are the similarities between the electromagnetic waves and the de-Broglie waves? What are the similarities? Okay, first of all, the similarity between the electromagnetic waves and the de-Broglie waves. Number one, both of these waves, they obey superposition principle. means two or more electromagnetic waves can combine to form a third new wave. Similarly, two or more de-Broglie waves can combine to form a new wave, that is called wave packet. And both of these waves, electromagnetic waves as well as de-Broglie waves, these waves can pass through vacuum. These waves can pass through vacuum. These are the two major similarities between the electromagnetic waves and the de-Broglie waves. However, just I am able to recall only two similarities. There may be more than that, but right now I am able to recall only these two. However, what are the differences? There are major differences. There are the major differences between the de-Broglie waves and electromagnetic waves. First thing, de-Broglie waves, these are electromagnetic waves, I would write on the left hand side, and de-Broglie waves or matter waves, I would write on the right hand side. First thing that we must note, that electromagnetic waves, these are associated with charged particle only. So only a charged particle can produce electromagnetic waves. On the other hand, de-Broglie waves are associated with charged particle as well as neutral particle. So this is the major difference. First major difference between the electromagnetic waves and the de-Broglie waves. So these are associated with charged as well as neutral particles. Then the second difference, even all charged particles do not produce electromagnetic waves. Only accelerated charged particles can produce electromagnetic waves. On the other hand, de-Broglie waves can be produced from particles at rest also, particles in uniform motion also, and particles which are under accelerated motion also. So means de-Broglie waves are associated with every particle independent of its state of rest or motion. On the other hand, electromagnetic waves are associated with the particles which have accelerated motion and which are charged. What is the third major difference? The third major difference is that electromagnetic waves are not deflected by electric and magnetic fields. Now, this is something which is quite interesting, and this property, if we study related with these de-Broglie waves, we have to make a conclusion, and whether the answer to this property is yes or no, and the actual answer is may or may not be. For that we must have some logic why the actual answer is may or may not be. Now look at this. De-Broglie waves are always in the form of a wave packet, and there is always a particle associated with a wave packet. Means whenever you say that there is a wave packet, matter waves, wave group or wave packet traveling in a region, then there must be some mass inside that wave packet, because de-Broglie waves are associated with a particle. Now if this particle is neutral, let us say this is a wave packet of a neutron. Now the de-Broglie waves associated with it, the particle cannot go outside this wave packet, and vice versa, the de-Broglie wave packet cannot be without that neutron. If I pass a beam of neutrons through electric and magnetic fields, that beam of neutrons will go straight. And if state in the sense means it will go undeflected. The statement word is not particularly correct here. I must say that the beam of neutrons will go through the region of electric and magnetic fields undeflected. And if the neutron beam is going undeflected, therefore the de-Broglie wave associated with this neutron should also go undeflected. On the other hand, suppose this particle is charged. Let us say it is electron or it is a proton. If I pass a beam of electrons through a region of electric and magnetic field, then we know that if it is a beam of electrons, it will be deflected toward the positive plate, and if it is a beam of protons, it will be deflected toward the negative plate. And same thing will happen with the de-Broglie waves also, because the particle cannot leave the wave group in which it is associated. So if the particle is going, let us say this is a beam of electrons traveling in this direction, and I have a positive plate here, negative plate here. So electrons will go straight as well as upward, because these are negatively charged, so these will be attracted by the positive plate. So the de-Broglie waves associated with the electron cannot go undeflected, because the electron cannot come out of the wave packet. So if electron beam is deflected upward, the wave packet associated with the electron should also go upward. In that sense, you should remember that the de-Broglie waves may be deflected, may not be deflected by the electric and magnetic fields. And not only that, when these show deflection, their deflection can be toward positive plate as well as toward negative plate. And who decides all this? It is decided by the particle to whom these de-Broglie waves are attached. It's quite interesting, and you should actually cherish this concept. You should remember this part, that this is an interesting property associated with the de-Broglie waves. What is the fourth property which is associated with the de-Broglie waves? It is that electromagnetic waves, these travel in vacuum with speed c, that is 3 into 10 raised to power 8 meter per second. So all de-Broglie waves travel in vacuum with the speed c, that is speed of light. This is something which is not obeyed by de-Broglie waves. An individual de-Broglie wave, let us say, an individual de-Broglie wave travels in vacuum with the speed Vp, which is equal to c square by v, which is always greater than c. So this is another difference between this de-Broglie waves and the electromagnetic waves. However, kindly remember that if large number of de-Broglie waves form a packet, then that packet travels with the speed Vg, which is equal to v, which is less than c. So this is, you should remember that the phase velocity of de-Broglie waves is always greater than c, that is speed of light, and the group velocity of de-Broglie wave packet is less than velocity of light. So this is a major difference, that de-Broglie waves can travel faster than the speed of light. This I have already discussed in my previous lectures, so I will not go beyond this point. It will be just an otherwise repetition of that concept again in this lecture. I would like to avoid that. What is the fifth point that is related with the difference between electromagnetic waves and the de-Broglie waves? The fifth point is that electromagnetic waves, these waves do not show dispersion in vacuum. That is, or you can say, or these show dispersion. These show dispersion in medium only, or you can say all electromagnetic waves of different wavelength or frequencies travel with the same speed. in vacuum. Now this is totally opposite in case of de-Broglie waves. What happens? The de-Broglie waves, they show dispersion in vacuum as well as medium. Now this is another major difference between electromagnetic waves and the de-Broglie waves. De-Broglie waves or matter waves show dispersion in vacuum also. It means the de-Broglie waves of different wavelength or different frequencies, these travel with different speeds in vacuum. Their speed is not the same. So that is another thing. However, I can write it in similarities. Now I have recalled third similarity also. I would just mention it here in similarities. So that, however, the type of dispersion shown by the electromagnetic waves and the de-Broglie waves is the same. Means both show normal dispersion. What is the meaning of normal dispersion? Higher wavelength lead to higher speed, and this is common, that the wavelengths which have high value, they will have high speed in case of dispersion, and the wavelengths which have low value will show low speed in case of dispersion. However, the nature of dispersion is same, but the condition under which the dispersion will be shown by de-Broglie waves and the matter waves will be different. That is, these show only dispersion only in a medium, and these show dispersion in medium as well as in vacuum. So I have just tried to compare similarities and the differences between the de-Broglie waves and the matter waves. So today I would sum up all these concepts related with the de-Broglie waves here, and I will now move to the next topic. That topic is very important when we will be studying Schrödinger equation. So today's rest part of the lecture is actually will act as a base for the Schrödinger equation. So I would advise all of you to just listen to this topic carefully, because it will be used frequently when I will be discussing with you Schrödinger equation in my lectures later on. So today I would again recall that wave function psi is calculatable, but it is not measurable or observable. So that leads to the statement which most of the teachers, including me, give in the class, that wave function psi has no significance in itself. Okay, that creates an interesting question in our mind, that if wave function is not measurable, it has no significance, it can be only calculatable. How it can be calculatable? I would just mention one-dimensional Schrödinger equation with you. It is d2 psi upon dx2 plus 2m upon h cross square e minus u and psi is equal to 0. This is a one-dimensional Schrödinger equation where h bar or h cross is Planck's reduced constant. Since you might have might not have the knowledge of this h bar, and if you have not attended my previous lecture, I would write this equation in terms of h also. So it will be 8 pi square m upon h square e minus u psi equal to 0. You will be able to transform this equation into this equation just by putting h bar is equal to h upon 2 pi. And this equation most of the students might have seen in their chemistry subject at the school level, and this is one dimensional Schrodinger equation. Now just I want to tell you how I have made this statement that psi is calculatable. Now if we look at this and we try to compare it with a famous equation of simple harmonic motion, d2y upon dt square plus omega square y is equal to 0. Both of these equations appear to be very similar just by making this transformation. If I put psi equals to y, x equals to t, and this quantity 8 pi square m by h square e minus u is equal to omega square. If I put these transitions, then both of these equations would start appearing similar. So why I did write this equation, because students at their school level have studied this equation of a simple harmonic motion and they have already solved it. The solution of this equation was given in their school level as y equals a sine omega t plus b cos omega t. If you have not solved it, it is very easy to solve it also. I will not go into the way how this is simple harmonic motion equation was solved, because that is not the topic of discussion for me, but I am just trying to tell you that psi is calculatable. It is a mathematical function. Now if we solve simple harmonic motion equation, we get in this equation actually y is being differentiated with respect to t, and omega is something which is related with the properties of the system. Or we know that omega is equal to square root of k by m. We have to remember some important basic level concepts. This k is a measure of elasticity, m is a measure of inertia, omega is the angular frequency of motion of SHM, and if we just write this equation, we can see that angular frequency depends upon the inertial and elastic properties of the system. So this omega is actually decided by the system under motion. So similarly, if I solve this differential equation, I would get two constants of integration and y as a function of t, and omega will be my answer. Similarly, if I solve, now I will erase this. Now if I solve, I am also going to erase this part now. Okay, if I solve this Schrodinger equation, you see this is a one-dimensional Schrodinger equation. Actually, we would study the three-dimensional Schrodinger equation in the discussion. Now you see this psi is being differentiated with respect to x. 2 and h cross are constants. M is mass of the object. E is total energy. Psi u is potential energy. All these three factors are actually defining the properties of the system to whom this Schrodinger equation belongs. I have not mentioned that system. That system will be discussed later on under the title of the lecture, that what are the applications of the Schrodinger equation. But one thing is sure, that Schrodinger equation is a second order linear differential equation. And if somebody is able to solve it, it appears to be very similar, since I have just it appears to be very simple, since I have just written equation of SHM, but it is not so simple to solve Schrodinger equation at all. It's just very important or a challenging task in front of a researcher. So that for a bigger system, for a system containing many particles, the Schrodinger equation needs high performance computers for solving. If you go to spectroscopy, or you see, if you have ever heard about density functional theory or Hartree-Fock equations, and you will see what is the demand of a hardware in those techniques of handling the Schrödinger equation. You can just Google it and find. Okay, the solution of this equation is not simple. However, let us assume that we have found its solution. So what will be the solution of this Schrödinger equation? Since it is a second order linear differential equation in which psi is being differentiated with respect to x, and these are the properties of the system, then therefore the solution must give us psi as a function of x and t with some constants and some properties e, u and m may appear in that solution, and some two constants, because it is a second order linear differential equation, at least two constants per particle of the system must be appearing in this solution. In general, if I would have written three-dimensional Schrödinger equation, then I would get psi as a function of x, y, z and t, and in this solution there might appear e or m or u and some constants in the solution. So this is just the end result of the wave function, is just the end result of a process. That process is nothing but solving a second order linear differential equation. So if it is the end result of a process of solving a linear differential equation, obviously this is justified, that wave function is calculatable, but it is not measurable. Why? Because we will see that the units of wave function, it's just one of the simplest concept that I am telling you. I will not go beyond that. But only one thing that I would just mention here, if we just see after solving this, we find its units will be 1 divided by square root of length in one dimensional problem. Now this is quite surprising. It is not possible for a physicist to interpret what is the square root of length. We cannot interpret it. So it cannot be measured, although it has been calculated. So therefore the wave function is not measurable or observable, and it has no significance in itself. If it has no significance in itself, it cannot be measured, then why we are still interested in wave function? That is a question of $100, and we would just mention that why wave function, although cannot be measured, although it does not have any significance, then why it is still an important parameter for us. This question must be answered by us. So for that we must go to some basic things. This question I can just tell this answer right now, but I would not wish to answer this question right now, because I would first develop the proper environment, so that when I answer this question, so then you will really be in agreement with me. Then only it will be a good thing to answer that question, and let us reach that situation. For that, please remember that this question, why a wave function which is not measurable, which has no significance, is important for us. This question has to be answered. I will answer this question later on. And also you remember that I have given this in my, I think, second lecture related to the de-Broglie hypothesis, that the wave function square has some significance. It represents probability density of the measuring the particle at a given place. Okay, now let us go to operators in quantum mechanics. Operators. So before discussing operators in quantum mechanics, I would just discuss simple operators that we are already familiar in our school levels. However, we did not use the term operator with them, but these are quite good operators. Let us see. We can say, first of all, what is the definition of an operator? Operator can be said as any process Normally it is for us, for a quantum mechanics teacher or a student, for us that procedure is of course mathematical procedure. So operator is any procedure, any process which will change one function into another function. Any process which changes one function into a new function is called operator. That process is called operator. For example, please remember constants are also a sort of functions which do not depend upon any variable. I can define constant as a function. In this statement, I can give this kind of statement. A constant is a function which does not depend upon any variable. Okay, let us take this question. I would use the capital letters. I can use special symbols for operators also. Let a cap is an operator, and this operator is nothing. This is square root, and if you want to understand it, do not call it square root, call it as square root of, and I would put some dots. This. So this is an incomplete statement. Square root of. So this is square root of. What is a cap? Square root of. Now this a cap is an operator whose process has been well defined. What is the process that has been well defined in this? Means whatever argument, whatever input will be given to this operator, that operator is a square root, it will just take its square root. For example, if I write a cap 2, kindly remember a cap and 2 are not multiplied. Actually, you must read it as a cap of 2. This of comes from here. A cap of 2. Now, if we remember this statement, it will, this when expanded, instead of 2, okay, I would take it 2, then this will become square root of 2, and the answer will be 1.732. Now look, operator in itself has no significance. Operator in itself has no significance, but when same operator gets some input value, it changes its input was 2 and the output is 1.732. Similarly, what will be a cap of 4? It will be square root of 4, that will be 2. Now, it is, kindly remember that a cap here 2 for me is a function. I can write it as a cap psi, which is equal to square root of psi. If I put psi is equal to 2, the answer will be 1.732. If I put psi is equal to 4, the answer will be 2. So in these two cases, psi was a constant. I could have also psi a cap of psi, and if I put psi is equal to 4x square. Now look, this psi is a variable, it's a function now. But this operator will apply similar process on 4x square now, and the answer will be 2x. So this is the input and this is the output, and this input has been changed into this output because of the contribution of this operator, that is square root. This transition is possible because of square root. So this kind of operation is a operator operation. So kindly remember that a cap psi and psi a cap are not equal. It is not good to write wave function before operator. If I write wave function before operator, it will be multiplication. It is a psi multiplied by a cap. If I write a psi after a cap, then it is not multiplication. This is square root of psi, and this is psi multiplied by square root of dash dash dash. Now since this dash 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 is still missing, so kindly remember, if I multiply, this is a multiplication, this is an operation, it will give me answer, but it is not giving me answer. What is this? It is a new operator. So if we multiply operator by something, that something will be written before the operator, and that will still be an operator, means input or argument is still missing. So kindly remember, a cap psi and psi a cap are not equal. Both of these have different meanings, and the student must be aware of this thing. So please keep it in mind. Let us now go to next operator. This operator is differential operator. Look at this. D, let us say a cap is equal to d by dx. How would you read it? It will be read like this. We can, it is, what is this process? If I want to make this process in the term of statement, then I would give this statement: differentiation of dash 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 with respect to x. Now this dash 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 will be the argument. Let us see, if I have psi is equal to sine 4x, then what will be a cap of psi? It will be d by dx of psi. It will be, in terms of statement, it will be differentiation of sine 4x. This dash 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 is now filled with respect to x, and obviously it will be d by dx of sine 4x, and it will be 4 cos 4x. Is it okay? Now let us take a cap is equal to d2 upon dx2. Now this is very interesting property of operators, that it is d by dx multiplied with d by dx. We can rather, let us say this operator is b cap. So this b cap is second order derivative, means I would not write this kind of statement right now. I guess that the students are now mature enough to make similar kind of statements. Okay, this will be second order derivative of dash 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 with respect to x. Now it's interesting to see that this operator is a cap and this operator is also a cap. So it is a cap square. So this is allowed in quantum mechanics, that if you multiply two operators, the result can be a new operator. So what will be this answer if I just apply b cap on the same wave function? Let us say psi is again sine 4x. Therefore, what will be b cap psi, which can be also written as a cap square psi, which is d2 upon dx2 of psi, which is equal to d2 upon dx2 of sine 4x, and you would get it minus 16 sine 4x. This will be its answer. So it is a simple method. I would not give its steps. The final answer will be this. You can verify very easily. So this is another property of the operators. Now let us go to next thing, which is called linear operator. Linear operator. Linear operator. So an operator is said to be linear if it obeys this property: a cap of c1 psi 1 plus c2 psi 2 is equal to C1 A cap psi 1 plus C2 A cap psi 2. Now where C1 and C2 are some constants on which operator A is not active. Initially when I gave the starting operator, that was square root, that square root can act on constants as well as variables, but there are certain operators which does not take into account constants when these are multiplied with some functions. For example, differentiation is one of them. So if I have some constant multiplied with the function, that constant will be taken out and the derivative will be taken only of a function. So it is this kind of example here. So left hand side is operation of the linear combination, this kind of sum in which two wave functions are firstly multiplied by some constants and then these are added or subtracted, is called linear combination. C1 and C2 are called weight factors, or it are also these are also called expansion coefficients. So if I would just spell it like this, this is the sum of operation, sorry, left hand side is the operation of the sum and right hand side is the sum of the operations. What the left side says? Left side says firstly you obtain this answer, means multiply C1 with psi 1, then multiply C2 with psi 2, then add them, then you will get a new wave function, then take its operation. And right hand side says that take operation of psi 1, multiply it with C1. Take operation of psi 2, multiply it with C2. Then the two answers that you get, you must add them. And if in both of the cases the final answer is same, then such kind of operation, such kind of operator is called linear operator. For example, let us take this example. Let us say A cap is d upon dx. Now we know that d upon dx of psi 1 and psi 2 is equal to d upon dx of psi 1 plus d upon dx of psi 2. So we know that the differentiation is distributed over sum. Rather instead of sum it can be minus also. So I have just taken C1 and C2 equal to 1, but you can take these as any constants. So differentiation operator is a linear operator. Kindly remember, all differential operators are linear operators. Similarly, all integration operators are also linear operators. Let us now take an example of a non-linear operator. Let us again go to square root. Let A cap is square root now. Now look, what would be A cap of 2? Sorry, what would be A cap of 4? Everybody will be able to understand this concept now. That is equal to square root of 4 will be, that will be 2. And what will be A cap of 9? That will be square root of 9. That is equal to square root of 9, that will be 3. And what would be A cap of 4 plus 9? That will be equal to square root of 13, which will be something related with the 3 point something will be the answer. You can check it on the calculator. Now what is left hand side? That is A cap of 4 plus 9 is not equal to right hand side. That is A cap of 4 and A cap of 9. Their sum is not equal to A cap of 4 and 4 plus 9. So therefore square root is not a linear operator, it is a non-linear operator. So this we must remember. And it is very interesting to note that the operators that we use in quantum mechanics are linear operators. That is something which is very important property, that the quantum mechanics uses linear operators. Let us now discuss eigenvalue equation. . or I would discuss in these three cases, that is eigen function, eigen operator and eigen value. Okay, the definition is very simple. Eigenvalue equation, this definition is very simple. So what is the definition? If an operator A cap is applied on some wave function psi, and in the result we get some constant, that constant may be real, may be complex, please remember, but it will be constant of the system. If I operate a wave function psi with some operator A, and in the result I get same wave function psi, and you remember this wave function and this wave function should be exactly identical, and in the end result of the operation you get same wave function psi multiplied with some constant, then such kind of equation is called eigenvalue equation. The operator in this case is called eigen operator. The constant that we obtain is called eigen value, and the wave function that we obtain is called eigen function. So eigen operator, eigen value, eigen function, and this whole is called eigen equation. Let us take off some examples, and I would give some more minute details which usually students ignore. Let us take an example. Let us say A cap is equal to d2 upon dx2. Let us say psi is equal to this sine of 4x. I have already completed this example. I would just write this equation. Now what will be A cap psi? You know that it will be minus 16 sine 4x. Now look, this sine 4x is in the output also, and sine 4x is in the input also. Now A cap psi is equal to minus 16 sine. We can write this. So this is an eigenvalue equation. So A cap, which is second order derivative, is an eigen operator. Psi, that is 4x, it is an eigen function, and 16, that is the constant value that I obtain after this result, is our this eigen value. Let us now take another example. Suppose I have A cap of is equal to d by dx. This is the first order derivative of something with respect to x. Let me take psi as e raised to power 4x. Now this is the wave function. If I write A cap of psi, it will be d by dx of e raised to power 4x. It will be 4 e raised to power 4x. So that is nothing but 4 psi. So I can write it as A cap of psi is equal to 4 psi. So this A cap, that is d by dx, is my eigen operator. This 4 is my eigen value, and this psi, that is e raised to power 4x, is my eigen function. However, quite interesting thing can be noted in this example. Let me now change wave function, which was e raised to power 4x, now equal to sine of 4x. Let us see what shall we get. Now if I write A cap of psi, it will be d by dx of sine 4x. That will become 4 cos 4x. Now you can see A cap psi is equal to 4 into psi dash, because this function and this function are not same, so it is not eigenvalue equation. So 4 is not eigenvalue, a cap is not an eigen operator, and psi is not an eigen function. Now, but what you should see that in both of these examples, the operator was the same. It was d by dx in this example also. A cap is still d by dx in this example. So we can make a conclusion here that an operator which is acting as an eigen operator in for one function may not be eigen operator for another function. So its all operations may not lead to eigenvalue equation. That is something which we must remember. So it means the choice of the function and the operator for a particular problem to obtain eigenvalue equation may not work at all when we are going to discuss another problem. So there we may have to formulate different operators and different wave functions. Either you have to appropriately choose operators or you have to appropriately choose wave functions. In most of the cases, the quantum mechanical operators are fixed. Means, for example, energy operator is always the same. The momentum operator is always the same. Hamiltonian operator is always the same. The only thing therefore we have in our hand is to choose appropriate wave function so that the eigenvalue equation may be formed. So it is an interesting part in our example which showed that you may not get eigenvalue equation from the same operator for all wave functions. So the simple or the straightforward conclusion drawn from this example is that different problems will give you different kind of wave functions so that eigenvalue equation is formed. A simple wave function of one problem may not fit into another problem. So you have to find the wave function of that. Okay, we have now discussed eigenvalue equation and we have now the knowledge of eigenvalues. Kindly remember, this equation again appears to be very simple on the board, but it's a challenge for a researcher at quantum mechanical level because you have this equation actually a cap psi is equal to alpha psi is normally a matrix equation, and if you are right now a student of graduation class, you know that in case of matrix equation, if you convert the matrix into a diagonal matrix, then the diagonal elements of that matrix will be the eigenvalues, and therefore you have to resort to diagonalization of the matrix. That is it in itself a separate branch of mathematics, matrices and determinants, where the diagonalization is done by using proper row and column operations. I will not go into those details, but kindly remember, for each particle of the system you will have different eigenvalue, and if there are, let us say, different 40 particles in the system, then the wave function will solve a matrix in which there will be 40 rows and 40 columns, and the problem of diagonalization of such a matrix which has 40 rows and 40 columns on the paper or on the board with the pen is almost an impossible task for anybody. So therefore this kind of diagonalization and solving eigenvalue equations for real value problems is a task which has to be handled with high performance computers. So therefore this equation appears to be very simple on the board, but it is a very tough task to solve in the real life. Kindly remember, this alpha is actually should be written like this, alpha, this is a symbol for matrix. Actually it is a matrix equation. So this is just for your kind of knowledge. Let us now go to the operators in quantum mechanics. let us take one example. Suppose I have a wave function psi equals a e raised to power minus iota omega t minus k dot r. Now this is the standard wave function that I will be using from now onwards for every problem. Although I have just given now that single wave function cannot be appropriate for all problems. However, just to start, this is the standard wave function for a wave, but we can modify this wave function by having different values of a, k and omega and r. So it will be just customized for different problems. Means we will solve the values of this eigenvalue equation will be formed subjected to the condition that a will be suitably chosen so that eigenvalue equation will be is applicable. So let us say this is a standard wave function for me. Here omega is the angular frequency of the wave packet and wave function, and this k is the propagation constant, r vector is the position at which the discussion is being made. So kindly remember that in whole of this discussion r vector will always be mean equal to x I cap, y j cap and z k cap. K vector will always be equal to kx I cap, ky j cap and kz k cap, and this k dot r will always be equal to kx x, ky y and kz z. Moreover, you should remember that I will be using this iota also, which is mentioned here also, which is square root of -1. Kindly do not confuse iota with I cap. This I cap and this iota are different. I cap is a unit vector along x-axis and iota is square root of -1. Kindly note these 4 things on your notebook because I will not be giving this explanation again and again. However, I will be using it many times in my lecture. Let us now just try to give answer to one pending question in this lecture, that why wave function is so important for us, although it is not measurable. We are now approaching to that question closely. Okay, let me take an example. Suppose I take a cap, rather instead of a cap, I would use a new symbol, px cap. Let us say this is px cap. This operator is iota h cross curly by curly x. Curly by curly x is partial derivative. Now look, this is multiplication because I have multiplied iota h cross with curly by curly x. So when I operate this on the wave function, let us say this is equation number 1. So what will be px cap psi? Let us see. It will be iota h cross curly upon curly x of psi. It will be iota h cross curly upon curly x of a e raised to power minus iota omega t minus k dot r. Now when I take the derivative, it will be iota h cross, its derivative will be as such, a e raised to power minus iota omega t minus k dot r multiplied by curly upon curly x of minus iota omega t minus k dot r. Now look at this. This is iota h cross, this quantity, this quantity is a psi itself, so I can write it psi. Now in this quantity, minus iota will come as such, and omega t, since it is partial derivative, so derivative of omega t will be 0 minus, and k dot r, I have already written it. It will contain three terms. First term is kx into x, so that will give me kx into 1. Second term was ky into y, that will give me 0. Third term was kz into z, that will also give me 0. And if I just consolidate this, iota and minus iota, it will make 1. So it will vanish. I would get h cross. This is psi. This is kx, and this is 1 minus 2 minus, and iota into iota minus. Okay, this px cap is minus iota h cross. Now it will be okay. So there is 1 minus here, 1 minus here, 1 minus here, 3 minus, and iota into iota, that is iota square, that will be fourth minus. So if I multiply minus term 4 times, the answer will be plus. So this is h cross kx and psi. But in my previous lectures, I have told you that P is equal to h cross k, that is Einstein de-Broglie relation, one of the Einstein de-Broglie relation. If P is equal to h cross k, then what will be x component of linear momentum? Px, it will be h cross kx. Similarly, what will be py? It will be h cross ky. Now look, this equation px cap psi is equal to h cross kx psi is an eigenvalue equation. In this, px cap is an eigen operator, psi, this one, is an eigen function. This value h cross kx, which is, you can also write it as px cap psi, is equal to px psi. This value is eigenvalue, which is x component of linear momentum, x component of linear momentum of the particle. So this is a measurable quantity. So psi, which itself is not measurable, contains the information about measurable quantity. And what is the measurable quantity? It is the x component of the linear momentum. Similarly, I can have py cap, which is equal to minus iota h cross curly y. And if whole of this process is repeated for this operator, you would get py cap is equal to py and psi. So this operator gives me the magnitude of this y component of linear momentum. Similarly, I can have pz cap, which is equal to minus iota h cross curly upon curly z, and the reader or the viewer can verify that this pz cap and psi will be equal to pz and psi. So look, what is important thing for us, that I have a wave function which is calculatable, which is not measurable, but that wave function, which it itself has not any meaning, can give me the information related with x, y and z component of the linear momentum, and all these three are measurable. Let us now discuss another operator, three-dimensional operator. In these three examples, we were able to find the magnitude of the components of the linear momentum. Let me take now p cap is equal to minus iota h cross del vector. Del vector, if you do not have any knowledge about it, del vector is equal to I cap curly by curly x plus j cap curly upon curly y plus k cap curly upon curly z. If I put this value of del here, then I can very easily say that p cap, this is operator for total linear momentum. The earlier three operators were for linear momentum components. If I see this is minus iota h cross, if I put this value of del here, it will be I cap curly upon curly x plus j cap curly upon curly y plus k cap curly upon curly z. So if I take this inside, it will become I cap into minus iota h cross curly by curly x plus j cap minus iota h cross curly upon curly y plus k cap minus iota h cross curly upon curly z. Now this will be I cap px cap plus j cap py cap plus k cap pz cap. So p cap is this. So this operator, which is this one, can be expanded like this one. So what would happen if p cap psi is found? Now remember, this operator p cap is a linear operator. If I write it like this, because it contains del is a derivative and all derivatives obey the property of linearity, that is sum of derivative is equal to derivative of sum. So this will be equal to iota, sorry, it's not iota, it is I cap px cap psi plus j cap py cap psi plus k cap pz cap psi. So we have already solved these three equations. It will be I cap px psi plus j cap py psi plus k cap pz psi. So psi, because it is just a mathematical function which has been calculated after solving the Schrodinger equation, so it can be taken outside. So we can take it common. It will become I cap px plus j cap py plus k cap pz, and psi is taken outside. Left hand side is nothing but it is p cap of psi. Now see what is the end result. P cap psi is equal to p vector psi. This is again an eigenvalue equation. So p cap, which is equal to minus iota h cross del vector, is therefore an eigenoperator for the total linear momentum of the object. Kindly remember, it includes direction also. So this operator not only gives the magnitude, but it also gives the direction of the total linear momentum of the object. So let me go to next example, that is called Hamiltonian operator. Hamiltonian operator. What is that Hamiltonian operator? H cap. Hamiltonian operator. Now it has two different forms. One form is time independent form, and second form of H cap is a time dependent form. Let us now discuss first time independent form. So time independent form of H cap, it is called Hamiltonian operator, is minus h cross square by 2m and del square plus u, where m is the mass of the object to whom this wave function belongs. Del square is actually del vector dot product with the del vector, which is equal to curly 2 upon curly x2 plus curly 2 upon curly y2 plus curly 2 upon curly z2. Kindly remember. Now what will be h cap psi? I just want to find this answer. When h cap operates upon this wave function psi, what is my end result? Kindly remember, u is the potential energy of the object, and it will depend upon the problem. Let us say this wave function is solved for a simple harmonic oscillator, then u will be half kx square. And if this wave function is solved for a freely falling body, then u will be, for small heights, then u will be equal to mgh. So since the value of u is different for different problems, so instead of taking its value, we would take its symbol. So problem wise its values can be inserted. So let us now find h cap psi. Now what will be h cap psi? It is equal to minus h cross square upon 2m del square psi plus u psi. Now this del square psi, let me call it as equation number 2. Now del square psi is something which has to be evaluated cautiously, because what is del square psi? I would solve it separately. I would keep this equation 2 as such. Del square psi, I will solve it. It will be having 3 terms: curly 2 psi upon curly x2, curly 2 psi upon curly y2, and curly 2 psi upon curly z2. Let us say this is equation 3. Now this is again a big equation. I would solve its first component, first term initially. So let us now find its first derivative. Curly psi by curly x. It is curly by curly x of psi. Put the value of psi from equation 1. It is a e raised to power minus iota omega t minus k dot r. Kindly remember, k dot r is equal to kx into x plus ky into y plus kz into z. Now if I take its derivative, it will be a e raised to power minus iota omega t minus k dot r itself, and the derivative of argument, that is minus iota omega t minus k dot r. Now look at this quantity is psi itself, so I will write it psi itself, and this quantity, let me write it square bracket here. So it is the partial derivative with respect to x. So what is the meaning of this? This quantity will be equal to, I think I forgot one bracket here. It has to be there, and there should be one bracket here also. So this will be minus iota outside. Derivative of omega t will be 0. Let me put a curly bracket here. Let me put a square bracket here. So it will be 0 minus, let me put a round bracket here. So k dot r, its first derivative will be kx into 1, second derivative will be 0, third derivative will be 0, then I can finish these brackets. Now what would be this answer? It will be minus and minus, it will be plus. So it will be iota kx and psi. Let us say this equation number 4. So my first derivative, curly psi by curly x, is iota kx psi. Now I will differentiate equation 4 again with respect to x. So curly 2 psi upon curly x2, it will be iota kx being constant will come out of the differentiation. It will again become curly psi by curly x. Now this curly psi by curly x we have already solved in 4. So put this value of curly psi by curly x here from 4. That will be iota kx, and this curly psi by curly x is nothing but iota kx and psi. Now iota and iota will become iota square, that is minus 1, that is minus kx square psi. So I have solved just first term. Now what will be the second term? Second term, similarly, second term for equation 3, curly 2 psi by curly y2 will give me minus ky square psi, and third term for 3 will give me curly 2 psi upon curly z2 is equal to minus kz square psi. And now I can solve equation number 3. Now put all these values in 3, you will get del square psi is equal to minus will be common. It will be kx square plus ky square plus kz square, and outside it will be psi. Now look, it is very easy to understand that kx square plus ky square plus kz square, it will be nothing but it will be k square, that will be k square into psi. Why? Because we know that k vector is equal to kxi plus kyj and kzk. So in that sense, k vector magnitude square will be this. So I have solved del square psi is equal to k square psi. Now I can put this del square psi value into. So let us see what shall we get. If I put this value in equation number 2, your answer will be h cap psi is equal to minus h cross square by 2m, and it will be minus k square psi plus u psi. This minus and this minus will become plus, it will become h cross k whole square psi by 2m plus u psi. We know that P is equal to h cross k, Einstein de-Broglie relation, that will become P square by 2m and psi plus u psi. Now we know that P square by 2m is classical kinetic energy of the object. So this is, I can take psi outside, P square by 2 u and psi. What is this? This is classical kinetic energy. What is this? This is potential energy. This is psi. So kinetic energy plus potential energy, their total sum is always equal to total energy. So h cap psi is equal to E psi. Now this, therefore, Hamiltonian operator, which is the time independent part I have solved, is just giving me eigenvalue equation. Kindly remember, so it is the single problem of a particle. It is the single wave function which has been calculated but which cannot be measured. From that same wave function, I am able to obtain x component of linear momentum, y component of linear momentum, z component of linear momentum, and total energy of the particle. Mass is directly known to us. Time we impose on the system, at what time the problem is being studied. Time is something that we decide from ourselves. Mass is known to us, momentum has been known, and the energy has been known. So let us now discuss about the second part, the time dependent property of the Hamiltonian, the time dependent form of h cap. H cap is equal to iota h cross curly by curly t. Now what will be h cap psi? In this case it is very simple. It is iota h cross curly upon curly t, that will be a e raised to power minus iota omega t minus k dot r, and if I solve it I would get iota h cross, then square bracket, same thing again, a e raised to power minus iota omega t minus k dot r, and derivative of the argument. Since we have done this thing many times, I would just write the result straightforward. It will be minus iota and omega, derivative of t will be 1 and the derivative of all these three terms here will be 0. So this quantity is nothing but psi itself. So it will be iota h cross and psi and minus iota omega. Now this iota and this iota will make it iota square, that is minus 1. That minus will cancel with this minus. It will be h cross psi and h cross omega and psi. So h cross omega, we know that this is the second Einstein de-Broglie relation. H cross omega is equal to E, total energy of the particle. So h cap psi is equal to E psi. Both of the times I am getting same eigenvalue equation. So I can find the total energy of the particle either by using time independent or by using time dependent form of the Hamiltonian. There are certain circumstances I would not discuss right now in this lecture, under which we will be using time dependent and time independent problems that I will discuss later on, but this is not a part of today's discussion. So however, one thing I would just tell you, that in this expression I have used kinetic energy formulation equal to p square by 2m, which is classical kinetic energy, which is not the relativistic kinetic energy. However, in this discussion no such assumption has been made. So please remember, the result of energy given by this eigenvalue equation will be applicable at relativistic as well as non-relativistic cases. However, the result of energy solved by this will be applicable only in non-relativistic cases. Only this thing we should remember. So we are now in a position to give the answer to the question that I raised during the start of the lecture, and I would like to end up my today's lecture at this point by giving the answer to the question why wave function is important for us although it is not measurable. So now we can give the answer to this question, that the wave function is important for us because although it is not directly measurable, but when we solve Schrödinger equation for the wave function, then by using appropriate operator, kindly remember there is a different operator for different parameters of the system. For example, if one operator is giving me linear momentum, the same operator cannot give me energy. So we can extract the all physical parameters of the system which are measurable from the wave function by using suitable operators. So in that sense, wave function is very important for us, because although directly it is not having any significance, but indirectly it is telling us all the parameters of the system, provided we know the operator which can be applied on the wave function to extract that information. So in that context, the wave function of a system is also called state function. So please remember, from today's onward, whenever we will use the word state of a system, wave function is also called. These I would put 3 equal sign here. These are equivalent. State function and wave function are equal. So this is a question which is normally asked, why wave function is called state function? Because wave function can give the parameters, all physical parameters of a system, and if we know all physical parameters of a system, then its physical state is known to us. So therefore, if we know wave function of a system, we know state of a system. So from today's lecture or from today's discussion onward, we can without any hesitation say the phrase state function rather than wave function, and we can use them equivalently also. We may not just mention it, so we can simply call it as state also. From today onward, we can just say that psi is the state of a particle or state of a system. Of course, it is the physical state, it's not the chemical state, because chemical state of a system is given by these 3 parameters, PVT, and physical state of a system is given by simply psi. So wave function of a system is equal to physical state of a system. Hope you have enjoyed today's discussion. It was quite a lengthy lecture today, but it was important, so I just preferred to go unabated in this lecture so as to complete my today's discussion. Hope you will enjoy today's discussion, and we will meet again in the next lecture, and there we will be just going one step further toward Schrödinger equation. Hopefully we will be able to start the Schrödinger equation in the next lecture. Till then, thank you. Goodbye.